It's my pleasure to introduce our next speaker, Deputy Administrator of NASA, Pam Melroy, for a discussion on driving innovation, advancing quantum technology to benefit humanity. Deputy Administrator Melroy has served in that capacity for NASA since 2021. She's responsible for laying out the agency's vision and representing NASA to the Executive Office of the President, Congress, heads of federal government agencies, international and external organizations, as well as the communities. One of the facts that was particularly interesting to me in her bio is that she is one of only 2 women who has commanded the space shuttle, and she's taken 3 missions to space. These were assembly missions for the International Space Station. Please join me in welcoming Deputy Administrator Pam Melroy.
Okay, hello. It's my pleasure to be here. I'm very excited. Appreciate the warm welcome. It is incredible to be here with a global group of quantum technology experts. At NASA, I just want to talk about our mission for just a moment. I'd like to start out by saying that we're pretty busy right now. And I'd like to share a little bit about our mission because I think I'd like to put into context what we think quantum technologies will be able to do for us. But just in the last 2 years, we sent a human-rated spacecraft to the moon for the first time in more than 50 years. We collected samples from our Mars Perseverance rover that we are preparing and thinking about how to bring back to Earth. We launched 7 operational missions with astronauts to the International Space Station, which doubled the amount of crew time we had on orbit to do science and technology on the ISS laboratory. We launched several important Earth satellites and instruments that are giving us improved data on the Earth, and we made great progress on our X-59 X-plane. It's a demonstrator aircraft that's going to demonstrate the ability to go supersonic, and instead of a thunderous supersonic boom that rattles windows and breaks glasses, will sound like a door closing. And of course, who can forget the James Webb Space Telescope and the amazing images that we are seeing coming back from that. And perhaps, maybe you happened to see this weekend, that we brought a piece of an asteroid home and landed it out in the Utah desert. This is the kind of things we do at NASA, and it's amazing, but they're actually super hard to do. And we constantly have to be looking at technologies and how they enable our mission. And if you look ahead for some of the really challenging things that we're looking at doing, we're looking at sending people to stay and do science on the moon for longer periods of time, and eventually Mars and the rest of the solar system. So we're very focused on that strategy to enable sustained human exploration of the solar system. But we're also working on things right here at home, including reducing emissions on the airliners that contribute the most to emissions in our atmosphere by at least 30%. And of course, as I mentioned, returning samples from another planet and many other exciting things. And absolutely, we are going to need innovative and cross-cutting technologies that are going to benefit our mission, but also support life here on Earth. So I want to stop for a second and talk a little bit about NASA's history in this area. And of course, this is one of my favorite examples, actually, the basic understanding in the early 20th century about the nature of the atom and how it later on transformed so many technologies. It's a great way to draw the straight line between the fundamental research and then technologies that change our lives. And when you look at things like lasers, semiconductor detectors, and integrated circuits, they've obviously been transformative. And as you know very well, that deep understanding of the nature of the atom is going to take us to even more exciting places. So NASA, of course, has always been very interested in key technologies like the ones I described. And NASA actually developed and flew what could be considered the first class of quantum sensors way back on Pioneer 10 and 11. we flew a helium atom vector magnetometer. What was important about that is we used the nature of the helium atom to allow us to measure the magnetic field, not just its total magnitude, but its vectors. And that was critical. That was the quantum nature of that sensor. And of course, we've been flying similar kinds of sensors ever since. Most recently, a little more coming more into the present time, a few years ago, we started a quantum AI lab at our Ames Research Center in California to work on the intersection between quantum and AI technologies. That's called Quail. And then recently, we provided the world's first space-borne user facility open for research to develop quantum matter on the ISS. It's known as the Cold Atom Laboratory. So since 2018, that's provided the atomic, molecular, and the optical physics community with the ability to remotely produce quantum gases and ultra-cold atom systems in a microgravity environment. Why that's important, and it's core to the work we do on the International Space Station, is that when you take out the effects of gravity, you're typically unmasking and showing second, third, and fourth order effects that are not possible to see here on Earth. And so creating new structures, recently there was a bubble made of material, gases that were just the tiniest bit above absolute zero. And we think it's going to enable us to look at things like new materials. We're going to be able to create things in new ways because we're taking advantage both of quantum technology, cold atoms, and of course, microgravity. So another area that we've invested very heavily in is space-based clocks that enable the global satellite systems. They're absolutely critical to the communications technology here on Earth. And what you may not know is they're also critical to our financial and banking system. It's absolutely critical to have those very precise timekeeping systems. And this even reaches into the realm of aeronautics. Our Glenn Research Center in Cleveland is developing an airborne quantum communication test bed that's looking at free space quantum optical links between ground stations and aircraft. And that will, of course, provide both increased security with quantum authentication. I just realized I forgot to change my slide. Let's see if I can get it up. Can I get my slide up? Can you see it? Or did I go backwards? Oh no, let me go back. Sorry about that. Got so excited about what we were doing. So here we go. Yes, NASA's current use of quantum. So obviously meshing optical with quantum is really important. I'll talk a little bit more about that in a moment. So I am going to just kind of look at quantum information science from a big picture standpoint, from how it impacts NASA and the technologies we're most interested in. So we'll just start with quantum sensing. I mentioned the quantum sensors that we've been using in space, but I really want to emphasize how important it is, because one of the things that we're doing is we're studying objects in space that we cannot get close to. It's really one of the hardest things about space science. We're observing things from such a tremendous distance that it's incredibly important to try to develop technologies that give us substantially advanced orders of magnitude improvements in the ability to detect and sense things. And so what's incredible for that is some of the amazing things that we could do. We could look at exoplanets, which are planets around other stars, and look very closely for signs of life. We can also use quantum sensing to look inside other bodies, whether it's a star or another planet in the solar system. And that's something that's very hard to do. And we're also hoping we could use it to find the needles in a haystack, the asteroids or comets that could be a threat to Earth. So I'll go on with quantum computing. I think this is the one that's obvious because it really touches just about every industry at this point. But having the ability to compute with more speed and capacity and to look at novel problems is really important. As a technologist, I have learned that everyone always wants more power, they want more data, and they definitely want more ability to sense things and to run algorithms with larger and larger data sets. So, nope, there we go. And of course, some of the algorithms we think are actually going to start to apply. We're looking at applying them to some of our really difficult problems. We have a lot of issues with materials. We go to really, really cold places and really, really hot places, and sometimes we go both in the same mission. And so the ability to use quantum computing to really understand the nature of materials and to come up with new materials that are lighter, stronger, more heat and cold resistance are very important, not to mention the things everyone knows about, like improved battery technology. Now, communications, including navigation and timing, are really a super rich area for quantum technologies in space. So the advanced atomic clocks are awesome because they're incredibly compact. And when size, weight, and power is critical in a space system. And they're also robust and spaceflight compatible. They can improve triangulation here on Earth, of course, as we know, where you can actually get better estimates for positioning over the current GPS constellation, but they can also operate autonomously, which can aid our spacecraft that are flying far beyond the reach of GPS and other navigation technologies. So for example, we're looking at a telescope concept that could use infrared, optical, and ultraviolet to search for and directly take images of habitable planets around other stars. But we absolutely cannot do that without the precision that the several orders of magnitude in precision that atomic clocks can offer in the future. So currently, of course, we're using the current advancements in atomic clocks. I don't want you to think that we're waiting for the next round. We're also using atomic clocks today to look for dark energy and dark matter. So why does that matter? Well, we really don't understand it. There's a lot of theories out there, and we need the data to help us understand what's really happening. Dark energy and matter make up 95% of the universe, and we can't see it. We don't know how much there is, and we don't know how it's influencing everything around it. So understanding that is going to help us understand the motion of stars, the motion of the solar system, in the galaxy, and of course, the motion of our own planet. So in free space, quantum communications and nav will be based probably exclusively on optical. And so that's getting back to that marriage of quantum and optical, very important to us. Not just in aeronautics, which was the example I gave before, but we're really looking at space to ground and deep space communications and navigation. And that's really important to us as we start sending people out into the solar system. It's hard enough to do with the one at a time, the rovers, the other explorers that we've sent out there. When we start sending people, we absolutely have to have better capability than we have now. So the quantum networking technology is going to build on the successes that we've had in the laser communications and optical communications to have so many benefits, including improved data security, better energy efficiency, and of course, higher data. Like I said, nobody ever wanted less bandwidth, efficiency, and data. So we're very excited about each of these three areas and the impact that they are going to have on our mission. But there's one more that I really would like to add, and that's studying the Earth. And I'm going to give you a very specific example. So as much as we're an aeronautics and space agency, we are a climate agency as well. And the reason why is that we know how to study planets. And we are studying the Earth as a planet, all the way from bedrock to the top of the atmosphere and the interaction with the heliosphere. So we're looking at everything from wildfires to extreme flooding. And one thing that the data is telling us is that climate is changing, and it's changing fast. So one of the areas that's critical to us is the ability to model. And we need to understand so much of environmental research has been about looking in the rearview window and looking at the history of the Earth. But we're in a place now where we've got to be able to predict and go forward. And believe me, climate is not weather. It's a lot more complicated. But better weather models can actually still help us understand the potential impacts. And we are continuing to create models and gathering data about the whole Earth system to help us understand what's happening. And I'll tell you, if we cannot do it without improved computing capability. So those advances in data processing are absolutely central to this part of the role. But I want to give you an example, which is a really fun, very specific example of something that we could do. So we have GRACE, which is the Gravity Recovery and Climate Experiment, because you have to have a cool acronym, and the GRACE follow-on, GRACE-FO. So it's a set of twin satellites that trail one behind the other around the Earth, and they've been mapping the Earth's gravity field using microwave and laser ranging instruments, which is classical sensing technique for over 20 years. So you're like, okay, what's this have to do with quantum? Well, right now they're operating at spatial scales and sensitivities that can monitor gravity, yes, but what that tells us is actually it helps us find ice, groundwater, and where groundwater is depleted, even variations in vegetation and volcanic activity. We can detect that through gravity, through these sensors. And so this is really obviously very important data, considering how important all of those phenomenologies are to climate models. But their current spatial resolution is about the size of Texas, so about 300 kilometers. And we can map the entire Earth about once a month. Now, of course, at the time we launched it, this was eye-popping capability, but we're already thinking about what is next, and that is a quantum gravity gradiometer that will use the interference of laser-cooled atoms, a quantum sensing technique, of course, in a single satellite that's going to provide us a full order of magnitude, 10 times better spatial resolution, mass change data. And what that brings us to, of course, is the ability to allow Earth scientists to actually look at this water depletion, ice, vegetation changes, water table depletion in drought under the ground at spatial scales that are smaller than a county in Texas. So you can see understanding the Earth at the scale of Texas is important, but if you can get down to a county level, now you're actually affecting people's lives. You're giving them information that could save lives and improve everything from agriculture to just survival. So these are incredibly important capabilities to us. And this is one of those areas where quantum sensing, we think, is going to have an enormous impact. So I do want to talk about partnerships for a moment because they're really important to us. We consider that we are innovating for the benefit of humanity. And so what that means is we're looking for partners everywhere. We work with a lot of international partners, but we especially work with industry. We recognize that industry brings unique capabilities we want to leverage. We use our superpower as a government agency to integrate and to lead and to have the vision. We like to say that our rockets run on fuel, but partnerships are actually the fuel that drives NASA. So we're working to develop quantum gravity gradiometers, such as I just mentioned, quantum-enhanced atomic clocks, and inertial sensors. And we're also working with partners to have a quantum network. And we're exploring those advanced quantum algorithms for things beyond climate to include high-energy physics with our Department of Energy colleagues. So we're going to continue to support and encourage our partners, and that's really, really important. Where industry plays a very strong role, and I'll give you one simple example that we're really looking for help, is, so, all right, we built and demonstrated a deep space clock, but we need academia and industry to miniaturize and ruggedize those so that we can routinely send them to space. So it's really my hope here today, and one of the reasons why I'm here to share all the ways that quantum technologies impact our mission, is that if you see something that can help you that I haven't brought up, we definitely want to hear from you. So I just want to say that we think that this is an incredible future ahead of us with quantum technologies and how it'll impact NASA's missions in aeronautics, space, and human spaceflight. So in February of 2020, the National Quantum Coordination Office proposed a strategic vision for America to build the foundations for networking quantum devices and named NASA as a major player. So we're working within the administration to facilitate the implementation of that. And to that end, I'm really excited to make two announcements today. So the first one is that early next year, NASA's Goddard Space Flight Center in Maryland, nearby here, will open its new Quantum Engineering and Sensing Technologies Laboratory. So that's going to bring atomic physicists, systems engineers, and application scientists from NASA and NIST and our academic and industry partners together. So Goddard is one of our major space science centers, and they're really at the cutting edge of the intersection between engineering and science. And what they do is figure out, if we're trying to measure something or do something, how do we build a spacecraft or a space system that will support that? So that integration of those technologies into space systems is what they will be focused on, how to do that efficiently and effectively going forward. So stay tuned, we're gonna get some really exciting mission concepts out of there. In addition to that, later this year, NASA is also going to implement a Quantum Pathways for Spaceborne Climate Science Research Institute at UT Austin. So this is going to be very unique, and it's going to leverage all of the Earth science applications that will come and advance our understanding of the home planet and effects of climate change through quantum information systems. Through the basic physics and technologies for quantum sensors, early stage cold atom technologies to develop the next generation of interferometry-based systems to enable those unprecedented measurements in climate that are so important to us. So this is really going to be something that you see transitioning to our satellites that fly around the Earth and look at it and study it and inform our models. And more, there's more to what's going on than that. I've also approved 2 new quantum sensing studies from our Office of Technology, Policy, and Strategy, where the Office of the Chief Technologist resides, to bring our communities together and inform our path forward. So how are we doing that? We're taking the next step. The first one is co-authors with an interagency partners at the National Reconnaissance Office and the U.S. Space Force. So we're looking at those partners. We all have very distinct missions, but we recognize that we're all interested in quantum. And so we're doing a study to take a look at mutual interests, places where technology development will advance each one of our distinct missions. And the second study is actually more inward focused at NASA. Hopefully I've given you a sense of the breadth of what we do at NASA, from aeronautics to sending humans on to Mars at some point. We are doing just about all kinds of things you can imagine. And all those people are really busy and they don't always talk to each other about what they're doing. So I'm leaning on our chief technologist and the Office of Technology, Policy, and Strategy to inform a future agency quantum sensing strategy by looking all around the agency at everything that we do and identifying what are our top priorities and where are our gaps and what will benefit NASA and our mission the most. So we've already started looking at some areas that are really interesting. I think one of them is fascinating to me is propulsion. Not only does it take advanced computing, but in addition to that, it really requires an understanding of fluid dynamics. And we've got very strong classical expertise in this area, but it's still kind of a black art. So we're taking a look at how quantum computing approaches are going to be able to help us make more efficient propulsion systems for both air and space. So hopefully I've given you some thoughts about NASA's mission and how important the work that you're doing is. It's a key strategic capability for the future for NASA. And we're just looking at all the problems across the globe, everything from medicine, climate, technology, and so forth. So one of the things that we like to say, I'm actually a part of what we call the Apollo generation. I was inspired to become an aviator, a test pilot, a scientist, and an astronaut because of the Apollo missions. Well, we're launching the Artemis campaign to return humans to the moon, including the first woman and the first person of color. So we want to inspire the Artemis generation, the next generation of students who will look at what we're doing in space and be inspired to go into STEM careers that can make a difference. So we definitely want to partner with you on that. We know that we need a greater workforce that are quantum enabled and kind of like digital natives. Maybe, hopefully we'll have some quantum natives in the near future. So the next few years are going to be very exciting. And I can honestly say that in my decades-long career in aerospace, this is really the most amazing time that we've had. The advances in technology and the things that we're doing are more complicated, but they're also bolder, and they require us to work together. And I'm really looking forward to how we can work together with you and how you're going to contribute to NASA's mission in the future. Thank you.